All right, so that's fine. I think you see how this fits together once we do an example. So let's solve a PDE, okay, using this method. And so sometimes they'll be in this nice form. Other times they won't. So you may have to expand things out, especially in the case of like nonlinear wave problems. Sometimes they're just written down a little bit differently. So just like methods from differential equations, sometimes you have to rearrange things so that it's clear how to apply your solution method. Okay. So here's it's actually just a straight up linear PDE. It's just got variable coefficients in y and x, but guided by our discussion on the last couple of slides, that's our A coefficient here, that's our B coefficient, and that's our C coefficient here. Okay, so we have immediately the coefficients that should be the right-hand sides of our ODEs. Okay, the question is, how do we parameterize x0 of s, y0 of s, and z0 of s? Okay. Well, in this case, we need to look to our initial condition, okay? And our initial data in this case have that y is 0, okay? So we don't need to really have a parameterized function for y0 of s, because our function y is just going to be 0 along that whole initial data. X here, right, is in need of parameterization because we're varying X, okay? So X we can afford to parameterize as S in this case, okay? You just have to choose your parameter S so that as you move along it, you're moving along the direction that changes within your initial data, okay? So this is, think of our line here, X. We want to say that, well, as I move along S, I'm changing the value of X. The simplest way of doing that is just to set x0 of S to S. And if that's the case, then the initial data itself will just be given by G of S because X equals S. So then we can just plug in X equals S and we get G of S. So now everything lives in this, parameterized by S world rather than parameterized, well, defined by X and Y, okay? So we usually start then, in this case, with x0 of S equal to S. And in this case, remember that we want X and Y to be greater than 0. So we just make sure that we take S to be greater than 0 in this case. Okay. Also note that Y is equal to 0. Okay. So this implies that Y0 of S is equal to just 0. Okay. Because it does not change at all as we move along our parameter. And then since x0 of S is equal to S, this implies that z0 of S, which is our dependent variable or our solution variable in terms of the characteristics, is going to be equal to G of S, okay? It's really just saying I'm going to reassign X along the initial boundary to be S, and then that means that my initial data is given by G of S, okay? And so if you put all this together, you get your initial condition, which is that U of X equals 0 for G of X, and this is for, X greater than 0 and Y equals 0, okay? So now the thing that we want to check, okay, before we move on is the Jacobian, right? Because we have our initial condition, we can check our Jacobian, okay? So given initial condition, let's check our Jacobian. okay? How do we build our Jacobian? Well, remember it's x sub s, y sub s, x sub t, y sub tau, sorry, x sub tau and y sub tau, okay? And this, along the initial data, is going to be x0 prime of s, y0 prime of s, and then a of x0, y0 in this case, okay, because it doesn't involve z0 at all, and then b of x0, y0, okay? So we just plug it in and check if this all works out, okay? So what is x0 prime of s? What's the derivative of this?
1.
This is 1, yeah. Right? Okay. What's y0 prime?
0, 0.
0? Okay. And then what's a of x0, y0? So we go up here.
Also 0.
That's just 0. Okay, so, and then b of x0, y0 is
S.
s. Okay. So this determinant is then equal to s. And is that always non-zero on our domain?
Yes.
It is, because s is always greater than 0. So we're good, okay? So this is always non-zero. The Jacobian is always invertible, okay? And so we know that at least in a neighborhood, we can generate these characteristics emanating from the initial data, okay? All right, so next step, can I advance the slide? Okay, all right. So next step then is that we want to take our expressions for the coefficients and write down our characteristic ODEs. So what are our characteristic ODEs now? They're going to be as follows. dx d tau is going to equal a. What was a again? So I'm going to flip back here. It was just minus y, okay? So I really just write down the ODE, dx d tau equals minus y. And then remember that x0 of s is equal to s, okay? So it's going to seem a little weird. It seems like we're working with something that involves two variables. But the direction along which it changes is tau. So we're really only solving an ODE in tau, okay? And then we think of s like a parameter. So we don't really think of it like a variable in this case, okay? dy dx tau is going to equal x, and y0s is equal to 0. And then finally, I have that, let's see if I can move this thing. No, the toolbar is in the way. There we go. Okay. And then we have the dz d tau, excuse me, is equal to what? Well, if I go back here, I have that c is u. But remember, in characteristic land, I replace u with z. So I have dz d tau equals z. And then remember, my initial data tell me that z0 of s is g of s. Okay? That's my first step now. Okay, so now I got to solve some ODEs. Okay, what is the solution to these ODEs? Well, let's take the easiest one first, maybe. That's actually this one. Okay, and I get what? Z of s tau is equal to, if dz d tau equals z, z of tau is what?
A constant times e to the tau.
Yes, a constant times e to the tau. So I'll leave that space blank. So what should that constant be?
G of 0.
It seems like it should be G of 0, but remember that we've solved something where we have Z of S of 0 is equal to G of S, and we're really treating S like a constant. So the constant in this case is actually G of S, okay? Because we're just saying for each value of S, I'm going to have some differential equation in tau. And so it's fine. We can treat G of S like a constant, okay? Just like we'll be able to treat S like a constant up here, okay? The next one is a linear system, right? So the next thing we have to solve the X and Y ones together, okay? Anybody just know off the top of their head what the solution to this is? X tau equals minus Y, Y tau equals X. Second order differential, or it's a system of two differential equations.
Combination of sines and cosines.
Right. Yeah. So we could do this in a number of ways. I mean, one way is just to turn this into X tau tau equals minus X. So that means that X of S tau is equal to some function A of S times cosine of tau plus some function B of S times sine of tau. Remember, functions of S are constant in tau. So the constants could be functions themselves of S. And then this means, so then we can, just from this up here, we have that Y is equal to minus X of tau. So that means that Y of S tau is equal to minus A of S sine of tau plus B of S cosine of tau. Okay. So let's now plug in our initial conditions. Okay. We have that Y of S0 is equal to 0. And so this is equal to B of S. So that just implies that B of S is 0. And then we have that X of S0, okay, is equal to S. So that means that A of S is equal to S. So at the end of the day, what we get is that X is equal to S cosine tau, and Y is equal to S of sine tau. So sorry, minus.
I think the signs above are wrong.
Sign on this. Yeah. That's, I knew I screwed something up. Okay. Right. Sorry, I flipped the signs up here. Okay. So yeah, so we get X is equal to S cosine tau and Y is equal to S sine tau. Okay. Sorry, I had a sign error up here, but I fixed it now. Okay. So fine. So we're making progress. Now we have a solution, but it's just in terms of our parameters S and tau. And we don't want it in terms of S and tau. We want it in terms of X and Y. So the next step is to invert, okay? And so how do we invert this? So you may say, well, I don't know how to do this. You need to get X and Y functions that represent S, and some X and Y function that represents tau, okay? There are a lot of ways to do that in this case, but these are trig functions, you can use a trig identity here. So X squared plus Y squared equals S squared in this case, just because, sine squared plus cosine squared equals 1, okay? I get then that S is equal to either plus or minus the square root of this. But because s has to be positive, I need to just take the positive part. I'm only allowed to take s greater than 0. Okay. For tau, what I can do is I can take y divided by x, for instance, and that's going to cancel out the s's, and I'll just get a tan of t, or tau, excuse me. And I get tau equals tan inverse of y of x, y over x, okay? So I'm almost there, actually. I'm not that far away now. I have tau as a function of x and y, and I have s as a function of x and y. And I have z as a function of x and tau. All I do now is I plug my functions of x and y into z, and I end up with, when I put everything together, that x and y is equal to z of s of xy, tau of xy. And so this is equal to what now? G of s, but I know what s is. It's the square root of x squared plus y squared. And e to the tau, where tau is tan inverse of y over x. Okay? That looked like a pretty harmless equation that we wrote down up front. This is a somewhat bizarre looking solution, okay? But using method of characteristics, we were able to just construct differential equations, sort of break this apart into parameterized ODEs, and then put it back together by inverting these functions, okay? So that's really the usefulness of method of characteristics, is you get solutions that you really probably could not guess. They would be hard to guess unless maybe you'd seen that PDE before. Okay. So the questions about this method. I have kind of maybe one more example that I would go through before the end of class. And then you'll have a chance to practice some on homework too. Go ahead. I think I heard something.
Professor, could you explain how you went from x tau tau equal to minus x to x and y?
This one right here?
Yeah.
So up here, how did we, so which step?
X tau tau equal to minus x to the next one, or y equal
How
to
did I
minus
go down here?
No, from there to the next one.
How did I go here?
Yeah.
Oh yeah, so this is me assuming that you've taken undergraduate differential equations and have solved this harmonic oscillator problem before. So, but the way you can do it, and the way it's typically done, is you say, well, x is, it's of the form e to the r theta, right? And then you plug it into this, and you get r squared is equal to -1. So then this means that r is equal to plus or minus I. So you get that x's, general solution looks like a e to the I tau plus b e to the minus I tau. And because you can construct trig functions from sums and differences of complex, of these, pure imaginary exponentials, then you can also write this as, a cosine tau plus b sine tau. Yeah. So I mean, I skipped some steps, but yeah, it's kind of like engineering differential equations. But yeah, I mean, I can point you to some resources if you need to review your undergraduate ODE material. Does that answer your question?
He's
Okay.
nodding.
Okay. All right. Sorry, I can't see you. All right.
Yes.
Cool. All right. So if there's no other questions on that, so let's